Now that we've got a bit of a handle on taking derivatives, we want to talk about applications. And so the first thing we're going to do is we're going to talk about an extreme on an interval, because this is going to give us one of the realistic applications of differentiation. Some of the most important ones being optimization problems. So this is something a lot of companies want to do, and what a lot of computer science and engineering people have to do. If you're thinking of just in a company, they want to ship a product in a certain container. What should you make the dimensions of the box be so that you guarantee it fits your product, but it also minimizes your cost? So maybe you have different material for different sides of the box. Each thing costs a certain amount. How can you possibly figure out what the best dimensions are going to be to minimize your costs? So to be able to do that, we need to talk about what are minimum and maximum values, because I want to minimize my cost. So we're going to look at a function, and we're given this function over a particular interval, so it's just going between 1 and 4. If we look at this function, we can see there's a clear value that is the absolute largest this function is, and there's a clear value that is the absolute smallest. So the largest value of f is going to be 4, and that occurs when x equals 2. The smallest value is 0, and it occurs when x equals 1. So we say 4 is the absolute maximum of this function, and 0 is the absolute minimum, because I never get higher than 4, I never get lower than 0. So this is our first definition. We're going to let c be a number in the domain D of a function f. Then the y value at c is the absolute minimum value of f if this y value is smaller than every other y value, regardless of the x you pick. We would say f of c is the absolute minimum value of a function on a particular domain D if the y value corresponding to c is bigger than all other y values for every x in your domain. So we have a lot of terminology to talk about these absolute max and mins. One possibility is you might hear them be called global max and min. You can hear them be called extreme values because they're the extreme y values that this function takes on. Now, not every function will have absolute max and min. It's a little bit of a tricky concept when you're talking about the absolute biggest this can ever be. So if we look at this function, I don't have an absolute max or min because this function continues up forever and it continues down forever. So sometimes it doesn't happen because we approach positive infinity as x heads in the negative direction, and then we approach negative infinity as x heads in the positive direction. But if I take a look at these 2 points that I have labeled, when x equals 3 and x equals 7, nearby, that is the smallest y value in that region. And this is the biggest y value around it. So sometimes we can't find extreme or absolute max and mins, but we can talk about them locally. So here, near x equals 3, the y value at 3 is smaller than all other y values around it. And likewise, near x equals 7, the function evaluated at 7 is the biggest it is nearby. So we would say these are min and max values locally. So really, the definition for local max and min doesn't change a ton from here. It just, instead of it happening for all x in your domain, it just happens nearby that particular value. So we say c is a number in the domain of D of a function f. Then the y value at c is a local minimum value if that is the smallest y value near c. It's a local maximum of the function if that is the biggest y value near c. Now, even though it's possible to not have absolute max and mins, if you restrict it and make it local, you might have functions that have no extrema at all. So let's consider the function y equals x. It is just a straight line. I have no points where this is the biggest y value around it. If I move on this side, I immediately get something bigger. If I move on this side, I immediately get something smaller. So I don't have any point that is bigger in a particular region. But if we've got all of these arbitrary functions and we've got all of these techniques, how can we possibly determine if something has extrema? And if it does, where are they going to occur at? So we're going to learn a couple techniques to kind of help us out. The first one is known as our extreme value theorem, which is abbreviated EVT. And so what this says is if you have a function that's continuous on a closed interval, keyword being closed interval, so it's continuous at the endpoints, then f attains an absolute maximum value, so some y value, and an absolute minimum value, somewhere in between this interval from A to D. And you notice these values that it can occur at are possibly at the endpoints. So this is something that's a little bit unique. You may have an extreme value at the endpoint of an interval. So I'm just going to give you two pictures to kind of visualize this. First, we're going to look here. I've got a function that's continuous on the interval from A to B. So I can equal those endpoints. I go up to it. I don't have to pick up my pencil at any point in between here. If I look, this would be my value that is the absolute maximum. So this is the value of C that corresponds to my max. This is the absolute smallest y value we have. So this endpoint gives us the value that gives us the absolute minimum. If you have something a little more complicated, you might have multiple places that maxes occurs. So these 2 points have the same y value. You have two C values that give you an absolute maximum. And then you have this point here where the absolute minimum occurs, okay? So as long as you have a closed interval, so it doesn't go off to positive infinity or negative infinity, it's some just particular interval, and you can equal those endpoints. If your function's continuous, you're guaranteed an absolute max and min, okay? Now on the flip side, if the function's not continuous, you might have no extreme values. So I'm gonna give you two examples. If I look at the interval from 1 to 3, and I have this function that has that jump discontinuity, so it's not continuous on here. What happens is I do have an absolute minimum that occurs at 3. So f of 3 equals 1 is my absolute min. But the problem is I don't have a maximum. It looks like it should be 3 as my absolute max, but I can't actually equal that. And this tells me I can get as close to 3 as I want, but I can never actually equal it. So I don't have an absolute maximum in this closed interval because it fails that continuity. If I have another function, this one's continuous on the interval from 1 starting at 3, but it's open, it's not closed. So it continues down forever and ever and ever and ever. I have no absolute minimum on this interval. I do have a maximum because the biggest y value I have is 3. So this is the absolute max, but there's no absolute min, okay? So if I know these occur, where can I possibly find them still? What do I know if they exist? This tells me nothing about how to actually find them. So that's gonna be our next goal. How can we find these extrema? And the important thing is gonna be something that's known as a critical number. So critical, it's important. A critical number for a function f is a number c in the domain such that the derivative evaluated at c is 0 or the derivative is undefined. So basically you have a flat tangent line at that point, or you have an infinite tangent line, or the tangent line doesn't exist. These points are what are super important to us. So if we have a local max or min at some value x equals c, c is immediately known to be a critical number. So critical numbers are really important because they're possibilities for extrema. So let's take a look at two examples. I've got a function, my absolute value. We know right here at 0, that is my absolute minimum. My derivative is undefined here. So f prime of 0 is undefined. Okay, and this is my absolute min. Okay, If I look at another example, I have a point right here, which is my local maximum. Another point here, that is a local minimum. So I'll call this C1, I'll call this C2. If I look at the tangent line here, it would be nice and flat. Tangent line here, nice and flat. So my derivative evaluated at C1 is 0. My derivative evaluated at C2 is also 0. So these points where we have critical values are possibilities for your local max and mins. They might be, they might not be. Okay. So we want to get some practice solving this, and then we'll keep working with these in future sections as well. And we'll also figure out how to find extreme values on closed intervals. But we're going to find the critical numbers of the function x minus 1 divided by x squared plus 4. So you want to figure out where the derivative is equal to 0 or where it's undefined. So in order to do that, we've got to go ahead and actually find the derivative of this function. So I've got the quotient of two things. I want to use my quotient rule. We get the low function d high minus high d low all over low low. So that would be divided by x squared plus 4 squared. Actually taking those derivatives gives us x squared plus 4. Derivative of the high function is 1 minus high. Derivative of the low is 2x. And then all divided by low, low. Okay. Distributing that out gives us x squared plus 4. Distributing that minus and the 2x gives us negative 2x squared plus 2x. And then all over x squared plus 4 squared. Okay. Combining my like pieces, that's x squared. I got a minus 2x squared. This is negative x squared plus 2x plus 4 divided by x squared plus 4 squared. And to make my life a little easier, because I'm going to set this equal to 0, I'm going to take out that minus sign to give me negative times x squared minus 2x minus 4. Okay. So we need two things. We need to see where does this derivative equal 0, so for what x values. The only way this fraction can possibly equal 0 is if the numerator equals 0. So to solve this, you could go ahead and set the whole thing and then cross multiply. You really need x squared minus 2x minus 4 to equal 0. That's a nice quadratic. We can go ahead and use the quadratic formula. That's going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. And then we just simplify. That gives us 2 plus or minus the square root of 4 plus 16. So you'd get 20 over 2. Just 2 plus or minus. Then you can go ahead and pull out a 4 to make this 2 root 5 over 2. That gives us 1 plus or minus root 5. Okay? So that's two possible critical numbers. Then you also want to see where this is undefined. So if you tried to set the numerator equal to 0, x squared plus 4 will never equal 0. There's no real number that happens. So x prime of x is never undefined. So this tells me my only critical numbers occur at 1 plus or minus root 5. So these are two important numbers which could possibly be local maxes and mins. Okay? So we're going to see applications of these critical numbers really soon, but they are possibilities for local maxes and mins. And we'll figure out how to test that. We'll learn about the first derivative test. We'll learn about a second derivative test. The last thing we're going to do in this section, though, is we're going to talk about a method to actually find extreme values on a closed interval. And so this is basically applying the extreme value theorem to give us the exact values of the absolute max and the exact value of the absolute min. So our closed interval method states to find the absolute max and min values of a continuous function on a closed interval, we do the following things. We first find the values of f at the critical numbers inside the interval from a to b. Then we find the values of f at the endpoints of the interval. Whatever the largest value is between step 1 and step 2 is the absolute max, and the smallest is going to be our absolute min. So this should say step 1 and step 2. Okay? But key thing, just like in all of our past stuff, when we've gone and applied the intermediate value theorem, when we've applied squeeze theorem, these are hypotheses that have to be satisfied. So I need to state my function is continuous and make sure it is, and I need to make sure I'm dealing with a closed interval. These are two key things that I need. So let's try one example. We're going to find the absolute max and min values of this function on the interval from 0 to 4. So first and foremost, definitely dealing with a closed interval, 0 to 4. And this is a polynomial. It is continuous everywhere. So now I can actually go ahead and apply this closed interval method. But I need to make sure I state that. So since f is a continuous function, on the closed interval, from 0 to 4, we can apply the closed interval method. Okay. So you need to make sure you state this. They are hypotheses to be able to use the method. So step 1, we have to find the critical numbers and then figure out what the y values are there. So to do that, we've got to take the derivative. So if I differentiate that, it would be 54 minus 6x squared. So now that we have that, the critical numbers are, we set the derivative equal to 0 because it's not undefined. Both of these are divisible by 6, and I'm going to get rid of the negative as well to make my x squared positive. So that gives us x squared minus 9 is equal to 0. That factors really nicely to x minus 3 times x plus 3. We technically have two critical numbers, 3 and negative 3. But I don't care about this one because it's not in my interval from 0 to 4. So I don't need to evaluate this. Okay. So we evaluate f at the critical numbers. So we go ahead and plug 3 back into the function, which would give us 5 plus 54 times 3 minus 2 times 3 cubed. So if you do that, you get 113. Okay? So this is a possibility for an extreme value. Step 2, we evaluate f at the endpoints. So we plug in 0 to give us 5 plus 54 times 0 minus 2 times 0 cubed. 5 is a possibility for an extreme value. Now if we plug in the other endpoint, that would be 4, 5 plus 54 times 4 minus 2 times 4 cubed. If you go through and do that, it's 93. Okay. From all of these possibilities now, I go ahead and look at what's the biggest, and that's 113. So this is the absolute max. And the smallest is 5, so that is the absolute min. Okay. In our next section, we're going to see another application of derivatives, which is also going to be 2 more theorems, and we're going to keep talking about these extreme values as well.